today I want to talk a little bit about representation theory of Juergens, and yeah, it's also closely related to the representation theory of quantum affine algebras, and about an application for the correlation functions of the infinite XXX chain. And yeah, let's go into the overview. So at first I want, yeah, yesterday you already heard a little bit about the story and about an application of the fermionic structure. Hermann told you about it, like fermionic structure for XXZ and how it can be applied to sine Gordon. And today I want to go a little bit more into the roots. So the story started in 2006 actually, and it started with the XXX model. Yeah, later could be generalized. So the first, what I'm going to do is trying to sum up the construction for the SL2 case. This is construction of recursion relations for the correlation functions of the infinite XXX chain. And yeah, we call it snake construction because it looks a little bit like a snake. And yeah, it yeah, has a very nice property, which is yeah, described by the so-called T-systems. And after I explain this a little bit, I want to give a short, I want to explain an attempt to try to generalize it to higher rank, especially SL3. Okay, so yeah, and this will be connected to the snake modules and extended T-systems. So some kind of extension. So the references I mainly use are, of course, the paper of Hermann, Jimbo Miwa, and Takayama. And it's about this construction of the recursion relations for the correlation functions of the inhomogeneous XXX model. I'm going to explain it. And yeah, the second important reference is the paper in 2012 of Muken and Yang. And this is where he introduces the extended T-systems and the so-called snake modules. Right. And I'm going to explain how the generalization of the snake construction can be used to calculate the residues of correlators. And yeah, especially using the result in 2018, again Hermann, Arthur, and Hazret, on the calculation of the correlation functions of the SL3 model using the RQKZ equation. And then, yeah, the fourth reference is just generally about how to write down the RQKZ in the general rank case, AN case. Actually, there's also like for any other symmetry an explanation, but I just need the AN case. Okay. So first of all, I consider the XXX Hamiltonian on the infinite chain, and it corresponds to the gapless case Q to 1 of the XXZ chain. And moreover, I want to yeah, consider the inhomogeneous chain generated by this kind of transfer matrix with M inhomogeneities. Right. So it is still exactly solvable, but the interaction is non-local. And the correlation functions were could be calculated in terms of multiple integrals via the vertex operator approach. There's a big book of Jimbo and Miwa. And yeah, and these multiple integrals could be continued for Q to 1, so in the rational limit. And later, Hermann and Föder proved the factorization. Okay. So yeah, so the first conjecture that was kind of surprising was that one could write the density matrix dm in terms of yeah, in terms of sums of products of one single transcendental function, omega, is what Hermann already mentioned yesterday, and some rational functions f. I leave out the indices, it's just to show you how the structure looks. And yeah. So the nice fact is, like, in the homogeneous limit, you will get odd integer values of zeta, and you find this kind of representation via the so-called Snell construction that I'm going to explain in the next few minutes. Okay.
Can you do one slide back, just to see where the inhomogeneities are inserted? Okay.
Here, like lambda 1 to lambda m.
From a certain point on.
Yeah, lambda 1, 2, 3 to m. And this is like where I want to, it's like an n-point function with m inhomogeneities.
The representation is the same at every site. Is 1/2 spin 1/2, say. What is the spin? It's just Pauli matrix.
What?
In the spin chain, what is the representation in every site?
Just spin 1/2, of course. Yeah. So just fundamental, usual spin chain that you all know. Okay. So yeah, of course.
You're thinking of n as finite. You're thinking of this n as finite, or the
So here it is taken. I just wrote down a finite transfer matrix, but we consider the limit n to infinity. So we want to use, like, I'm going to explain it. So we want to use some properties that can be proven via this vertex operator approach, and yeah. Okay. So yeah, So the result can be written in terms of transfer matrix over an auxiliary space of fractional dimension, which is quite funny. And it could be generalized to XXZ later. And this kind of reduction relation that was proven in this 2006 paper could be solved, and somehow it was possible to really write some fermions, and it's explained in the HDS papers of Hermann and Jerome Pasmino.
You will explain what it means later, these notations?
What?
In the conjunction, so you will explain later what all this means? The conjunction part, I mean.
And the fractional dimension also.
Oh, the generalization is not that far. So this is just generally a fact that somehow.
Okay, but what does it mean, like D1 M? What's
So the first line is just the definition.
Ah, okay.
Yeah, this is just a density matrix and density matrix, and you can put in some operator. This is just the components of the reduced density matrix. Actually.
This is like matrix basis or something.
Yeah, this is on the spin chain.
Oh, okay.
Yes, but where is lambda? Where are the inhomogeneities, or just lambda dependence in the second hand of the equation? It's inside.
Yeah, it's kind of inside.
Inside the vacuum.
Inside the vacuum.
Inside operators.
Okay, so let's go a little bit deeper into the material. The density matrix itself satisfies 6 very important properties, which are the global GL2 invariance, the R matrix relations, the left-right reduction relations, the RQKZ relation, and 2 more. But let me stop here because they are, the RQKZ is quite interesting. It relates the density matrix to itself by a shift, which is just 1. And I will draw it later. So So the important fact is that A is just a product of some R matrices such that, so because of the prefactor of the R matrix, I didn't say much about that, but it is this product of gamma functions, they kind of cancel out so the gamma functions somehow give some products that will remain as rational coefficients. Okay, so actually in this RQKZ relation, you only get rational functions.
And bar is charge conjugation.
Huh?
One bar means that you are doing charge conjugation on.
Oh no, it's just like new one space. So somehow what A does, it somehow takes the density matrix, multiplies with it, and gives a new space 1 bar, which is replaced. So here the density matrix has the first space 1 bar. Here it's just 1. Okay. Later it will be the anti-fundamental representation, but for now it's just 1 bar, which is again spin 1/2 representation. Okay. So yeah, as I said, the components also in the R matrix relations and in the RQKZ equation are rational. And as you know, the density matrix is translationally invariant. It fulfills the spin conservation rule. You should be quite familiar with that. And yeah, now using these multiple integrals, you can prove some analyticity properties. The first one is that the dm is meromorphic in the parameters lambda 1 to lambda m, and it has at most simple poles at lambda I minus j in z without 0 and plus minus 1. And yeah, it also has an asymptotic property, which is in the strip as delta. You can take the limit lambda 1 to infinity, and you will just remove, yeah, just one line in the density matrix will be just trivial. Okay. Right. And these 6 properties determine dm completely. So you can just take these 6 properties and do fancy stuff with it. And that's what the construction intends to do. Yeah, so using these 6 properties, so actually only 2, 3, and 4, which is the RQKZ, the R matrix relation, and the reduction relation, and the analyticity properties, we can show that we have another property, which I call the property 7. It's like projector times dm equals same projector times d with m with 2 less points. So it reduces dm to dm minus 2. This is really important because the construction will be very dependent on it. Okay. Yeah. I would. Let me postpone this explanation because I want to go a little bit more into the construction. Let's just keep this for granted for now and believe that this projection relation is true. Then we can do what we call Snell construction. And yeah, so the idea is the following. So we know that the dm is meromorphic with the most simple poles. And yeah, so for such a function, it is enough to calculate the residues and consider the asymptotic behavior. And then by Juergens, we can recover it somehow. So that was the basic idea of the construction. And yeah, so this is a little bit technical, but what is written here is that the residue of dm can be written in terms of like some operator times dm minus 2. And this operator is what I call Snell operator. And yeah, and this Snell operator is really the thing containing the single meromorphic it is a single meromorphic function in the parameters. Okay.
Is this X, is it related to the R matrix? R matrix somehow?
Yeah, it's some product of R matrix. R matrices, I'm gonna show a picture later. So it will be kind of looking like a snail, I would say.
Actually, it looks like you are doing a form factor bootstrap.
Yeah, it's quite related, I would say. Okay, so yeah, so the very surprising fact about this is that this operator in front of dm minus 2 is completely determined by the Kirillov-Reshetikhin module wk. So what is the Kirillov-Reshetikhin module? So for SL2 it's just spin k-half representation of some of the Youngian. Yeah. So this is really easy, but somehow only this irreducible representation contributes to the operator and no other. And yeah, then as I said, looking at the asymptotics, you could somehow, or that's what was done, they could somehow prove that they could somehow prove a recursion relation for the density matrix itself. Okay, so as I said, a few pictures. So here I just write how the RKKZ equation looks by applying it 2 times. I could just also apply it 1 time, but yeah, this is how it looks. And yeah, now as I said, I want to take the residue. And what happens if I take the residue? So in the red circle,
Could you explain just a little bit here? I'm not sure I understand.
So what I do? So these are the parameters of the density matrix, right? And I apply the RQKZ equation 2 times. It means I have a shift by 2. So here will be the density matrix, which has the first parameter shifted by 2, right? And yeah, so this is just the RQKZ equation. I just applied the RQKZ and nothing more.
Sorry, what is RKKZ?
Just what I...
We have very finite memory. Our memory is smaller than...
We're tired.
Yeah, it's just this kind of relation. I didn't say what A is. Maybe I am going to show it later. But yeah, just... A is just one loop. Okay?
But so, somehow I can't, I'm too slow, I don't get what it means.
So it means, so I have d of mu1 minus 3 is some A operator times d of mu1 minus 2, and again it is equal to some A operator times d of mu1 minus 1. Yeah, so applying this relation 2 times.
Can you write down it in graphical notation? This operation once just RQKZ relation.
Yeah. So if I get some shock, then I could do it.
There.
on the or also here. Yeah. There's a good one. He doesn't want to.
Sorry for my drawing skills. I really apologize. Okay, and here I have these lines. Closed.
I think the upper second last vertical line has to have an open end. You have to go through.
Something is missing. So
It's a little end. Yeah.
Right, we have like 3.
no, this was.
Yeah, that was correct. The upper part.
And the other one has.
Horizontal line to the
Just one more spin pointing into it, I guess.
No,
Go further down?
through.
We have like 3 lines.
Okay.
Oh, sorry. Yeah. So this is a little bit shifted. Okay. So. Yeah, I should shift it a little bit to the left. Okay.
I see.
Now it's fine. You can see that this is connected to that. It's not connected. This is the same line as that, and this line.
Mostly correct.
Yeah, sorry for my drawing. How it's here?
The snail operator is basically a shift in the space of the matrix, the rapidity.
Yeah. So let me try to continue because I want to explain a little bit more. So what happens if we take the residue of this? The R matrix in the red circle gives like a scalar factor times the projector onto the singlet. And yeah, we know that we have the relation 7, and we want to apply it. So what happens is, so this picture is understood as, so it's, so you can still draw what happens, but this here has to be understood as a limit. Mu1 goes to mu2 minus 1, and so the residue. Okay, so what you get, the first two lines decouple from the correlation function, and you get kind of this red box, which we call the Snell operator. Okay. And so I just pick this red box and do this several times, and I always get this kind of Snell operator, and I can rewrite it by connecting the two singlet and its dual again. So maybe I didn't say that. So we have the projector P minus on the singlet, and we can just rewrite it as a singlet tensor its dual, and this is why these two crosses with no vertices appear. It's just the singlet and its dual. Okay. So this is just a short way, tiny way of writing it. But so you can also equivalently take this picture. Okay. Doesn't matter if you decouple this singlet. So so what you see is that in this Snell operator there are kind of closed loops or fundamental representations of the Youngian, the Youngian, like. And so natural question arises is what happens to the to these representations in the line? So is there any way to understand it differently? And in fact, as I told you already, somehow only the Kirillov-Reshetikhin module WK decides what happens. So taking the residue at lambda 1, 2 at minus k minus 1, we get the Snell operator with k loops. And since every line can be regarded as a fundamental representation of the Youngian, we have to deal with the tensor product of fundamental representations. So so the first Kirillov-Reshetikhin module is just a fancy way of writing spin 1/2. Okay. So what we have is tensor product of spin 1/2 representations, and the loop parameters are written in the argument. Okay. So mu minus k plus 1, and so on until mu. So the funny thing is that these spectral parameters are actually in special position. So that's what Jules told you 2 days ago, I think. There's like a point where you have kind of fusion. It means you have a short exact sequence which doesn't split, but so you still have a short exact sequence, and somehow you can calculate the projectors and look what happens in the Snell. So let's for example take this case where we just have two loops. Then we have two fundamental representations, and that's why I wrote these two loops. Then we have this short exact sequence, and we can consider the projectors onto the subcomponents. And what happens is that the projector onto the trivial modules, W0, cancels out.
I don't know,
So-
what are those superscripts?
The dimensions. Not.
Dimension.
The Kirillov-Reshetikhin module WK, W0, W1 is spin 1/2, W2 is spin 2/2, and so on.
Ah, okay.
Okay, so it's Kirillov-Reshetikhin module index. Okay. Yeah. So what we are interested in writing the irreducible components of this kind of tensor products, and this is of all possible short exact sequences that appear in the Snell operator. Okay. So yeah. Mathematically, it is just an equation in the Grothendieck ring, and you can write it in terms of transfer matrices, and yeah, it looks like that. And you know this, maybe you have already seen it, and it's called T-system. So generally, we have this kind of T-system, this kind of T-system, the Kirillov-Reshetikhin modules, WK times another Kirillov-Reshetikhin module, WK with some shift, 1, is the product of the higher Kirillov-Reshetikhin module times the lower Kirillov-Reshetikhin module plus 1. So, yeah, this is what is called the T-system. And yeah, so the question is, how can this help me to understand what's happening in the Snell? So, as I said, for k equals 1, we have the two fundamental modules, and only the Kirillov-Reshetikhin module W2 survives. And what I can do now, I can take these T-systems and try to derive what happens if I have the Kirillov-Reshetikhin module WP, let's say p equals 2, and I want to tensor another fundamental representation. So, yes, another spin 1/2. Okay, so WP times W1, and I want to know what's that. And I can use these systems to derive this equation. So WP times W1 equals WP plus 1 plus WP minus 1 with some shift in the parameters. Okay? And yeah, and this is what really happens in the Snell. I take the WP, I tensor another fundamental spin 1/2 representation, and I get this.
The spin 1/2 representation is the dimension of this sort of line that you draw. This
Yeah, it's the lines in the Snell. Yeah.
But only one time, right? As if I do it twice.
Every line has a spin 1/2.
Yeah, exactly. That's a separate.
And what I try to answer is what happens in the tensor product. Okay. Yeah. So what you can do is you can try to write down the projectors onto these two subcomponents, onto these two composition factors. And yeah, so the funny thing is that the projector onto WP minus 1 cancels out. That's kind of
Sorry, isn't this equation of usual fusion?
yeah, this is kind of fusion. Yeah, right. Okay.
What do you mean the projector cancels out?
Huh?
What do you mean the projector cancels
So if you put in the projector, so you can do a partition of unity in these lines, and you can just multiply the projector in, and somehow because of these crosses that we saw, here, and because of this singlet, they give 0, just cancel.
What do the crosses mean again?
They are just P minus, projector onto singlet. And here it is actually P times P minus, so yeah, but P times P minus is proportional to P minus, right?
So you want to say by iterative use of this equation, you project onto the highest spin and all the rest goes to 0.
Exactly.
Right?
So now you're proving that your decoupling condition RQKZ or something, how it's called, it's true also for higher spin representations. That's what you're proving. What you're proving.
Sorry, I didn't.
You had the decoupling condition, that one you called, where you had D equals A times D with one less parameters. Right?
Yeah.
So now you are fusing,
Yeah.
and you are proving that this property will still hold for higher spin representation.
Right. Yeah. So I don't initially take higher spin for the lines. So what happens is I take these lines and I consider them as a tensor product. And what happens, like these lines are successively in special position with the next nearest neighbor, and they kind of fuse, and they fuse, and they fuse, and somehow the projectors, these ones, cancel out.
exactly on the high. Yeah, so you really get the fusion. You don't get the tensor product. You really get the fusion.
Yeah. Okay. So, okay, this is hopefully clear. And yeah, so the question I want to try to tackle today is, in the last few minutes maybe, how to generalize this for higher rank. So, first of all, we have to look at these properties. And we need the same properties in order to get like properties that completely determine also for higher rank the correlation function, right? And yeah, so yeah, property 1, 2, and 3 would be just GLN invariance and yeah, R-matrix relations and reduction relations. These can be yeah, they are generalizable. I don't want to talk about this too much, but yeah. So the question is about how does the RQKZ equation generalize? So that was what I said, is explained in the paper of Andreas and Hazret. Yeah. So what actually happens is, in the higher rank case, we have two kind of parts of the RQKZ relation. So we have one, so first of all we have to introduce another density matrix where the first vertical line is replaced by an antifundamental representation. So yeah, just let's say SL3, quark, anti-quark. Okay. Then yeah, and then we can relate, then we can find some kind of yeah, half RQKZ relation that relates D to D1 and D1 back to D. So yeah, I already wrote the combined RQKZ equation, and again you can write one part of it if you like. It's just, so it's really the same as this, but you just have to replace kind of one loop by either, yeah, you can have the fundamental, which would be the same as this, and the other one would be where you replace the loop by an antifundamental line. So it goes in here, and this would be then related to the density matrix with the antifundamental representation in the first vertical component. Okay, yeah. 5 and 6, the analyticity properties, yeah, they are also thought to have a, or yeah, it is not proven that they have a good generalization, but I think there is like also a vertex operator approach, at least in a massive case, and maybe it's possible to take limits, as in the SO2 case. But yeah, for now it is an assumption that these meromorphicity and the port structure somehow generalizes, okay? Yeah. And then, as you have seen, we need some kind of property 7, which was the protector property, so that we can do this snare construction again. So, yeah, actually, yeah, this kind of property exists, but it only applies to one of these two relations, one of these two parts of the RQKZ. So for the other part, we have to think of maybe another solution. So for SL3, there is an idea where a projector onto the antifundamental appears. So it's like fundamental. For SL3 project onto antifundamental, it naturally appears in this construction. But then you just have one line less in your construction, and the Snell operator doesn't really decouple, and then it's a little bit more difficult. Maybe I can show a picture later. Yeah. Yeah. The other residues, yeah, as I said, have to be considered separately, but every second residue is fine. It really has this projector, which is the complete analog of the relation 7, and this is good. Okay. Yeah. So as I said, for SL3, there is this kind of projector onto the anti-fundamental, and somehow you can use the RQKZ again to relate it back to D. And then what I did is, just using Mathematica, I could check the first few residues of D3 and D2, which was described in the paper of Hermann, Arthur, and Hasvet in 2018. And I can, of course, using D3 and D2, I can make a prediction on the residues of D4. Okay. Okay, now let's go back to the Kirillov-Reshetikhin modules and how this kind of generalizes. So first of all, we can just write the same thing. So even if it only exists, even if it only somehow decouples when I have the shift by 2n plus 1. Actually, the shift by 2k n plus 1. I can write the same object, and I can look at the same object and see if it has some nice properties. And yeah, so the question arises, which composition factors appear here? And does anything cancel out or doesn't cancel out? Yeah. So this would be a little bit technical. So Mukin and Yang, they introduced these snake modules, and they kind of describe, they kind of completely describe the irreducible representations of the Yangian via tensor products and direct sums. Okay. Yeah. So the important fact about the representation theory of the Yangian is that there is still a notion of dominant highest weights, highest loop weights. They are called loop weights, and for any the fundamental evaluation modules have the multiplicative highest L weights YIA. These are just some indeterminates Y, and they are multiplicative. And the other important fact is that any irreducible module is contained in the tensor product of fundamental modules, and for every monomial in the fundamental loop weights, we can define a unique finite dimensional simple module L of M. This will be important. And another very important thing about this module L of M is that we can assume the parameters, the loop parameters A, to be half integer valued. And this is what is explained here. It's because fusion is only happening when the loop parameters differ by half integers. And on the other side, there is this Hopf algebra automorphism tau A of the Yangian, and you can somehow adjoin the parameters back. So you can consider the half integer valued parameters only, and at the end you can get everything back by adjoining with tau A and considering tensor products. Okay? So this is very good, because now we can visualize these modules L of M on the lattice I cross D, which I call X. Okay?
Very nice question. So are there Drinfeld polynomials? Are these Y's?
Yeah, they are connected to Drinfeld polynomials, and the multiplicativity property is really related to the story about Drinfeld polynomials. But I didn't want to go into the very detail here.
So I can think of YIA as a maybe degree I polynomial in A or something like this?
It's in the fundamental direction I polynomial just degree 1 polynomial. So fundamental ones have degree 1 in the fundamental direction I.
Okay, right.
Okay?
Yeah, sure.
And the zeros is just A. Okay? This is the connection to Drinfeld polynomials. Right. So we can only consider the half integer valued parameters, and then we can visualize this module L of M on the lattice I cross D, as I said. And now we can define special modules by looking just at the lattice. So for any I comma k in X, a point I prime k prime is said to be in snake position with respect to I comma k if the difference of the k prime minus k is greater than 2 plus I prime minus I. And I, so sorry, maybe I didn't stress this enough. I is just the number of nodes in the thinking diagram of SLN. Okay.
Z is related to the degree of the in the loop.
It is related to the half intervalued parameters that I just assumed. Okay. So the loop parameter difference of the loop parameters is greater or equal to the difference in the Dinkin nodes. So how much steps I have to go in the fundamental directions, and actually perpendicular to the fundamental directions. Yeah, plus 2, and this is actually somehow where this fusion appears. So you may already notice that there is a plus 2 here. So I said half integer values, but I take z, so I forget about the half. So you have to always think of there's a factor 1/2. Like I don't want to always have a factor 1/2. It just makes it more complicated. Here's just like this. Okay. So here we are on this lattice. So don't confuse this. Okay. So the point I prime and k prime is in minimal snake position if it is the lower bound, and point I prime k prime is in prime snake position if it is between I prime plus I and I prime minus I plus 2. Okay. And yeah. Then of course we can define a finite sequence of points, and we say that this finite sequence is a snake if any successive point is in snake position with respect to the last one. Okay. And the same for minimal and prime snake. Okay. So there will be pictures. Okay, here's a good picture. This is like for A4. I just wrote a snake with 4 nodes. Would be the L of the product of the fundamental y2, 0, y1, 3, and y8, y3, 8, and y4, 8, and y4, 10. Okay? So you see that these points are in snake position with respect to each other. And so what can I say about these so defined snake modules? So I have these finite sequences, and the modules L of n, where I take these fundamental variables that satisfy the snake condition. I call them snake modules, and these have the special property that they are prime and real. So what does it mean, prime and real? Prime means that they are, as I said, they are irreducible modules, and a prime irreducible model is a module that you cannot write as a tensor product of 2 other irreducibles. And the real module is a module whose tensor product with itself is irreducible. Okay? And somehow these snake modules can generate all the other irreducible modules in the whole category using, as I said, the automorphism tau A. Okay? Right. So what I want to do is I want to write down some kind of relations, Schrödinger sequences, which are now Schrödinger sequences between these snake modules. And so what Mukin and Young did, they took the prime snake and wrote down these Schrödinger sequences. So what is that? So first of all, for any prime snake, you can define a neighboring snake, actually 2, one to the left and one to the right. And then you have an extended T-system, which is like L of the first snake times L of the second one, is like okay, so I have to say what these snakes are. So first of all, we have the snake, the first snake is like, let's consider some snake, and then I can cut the lowest point in the diagram, and I can cut the most, the point at the top from the snake, sorry. And it will be a shorter snake. So this one is where I cut the head, and this one is where I cut the tail. And this one is where I cut head and tail, and this one is where I cut, where I leave it as it is. And this one is one of the neighboring snakes to the left, I think, and this is the neighboring snake to the right. So this kind of system is satisfied. And yeah, let me draw a picture. It's a little bit easier. So this one has cut its tail, this one has cut its head. This is the whole snake, and this is without the head and tail, and these are the ones with neighboring snakes to the left and to the right. Okay, these kind of funny extended T-systems is what Mukin and Young proved in 2012. So, okay, now we are through the kind of technical stuff. Yeah. So, one remark is the following: is extended T-systems, they include the T-systems that we saw for the Kirillov-Reshetikhin modules. So the Kirillov-Reshetikhin modules is just if we take straight lines in one fundamental direction. And then we get back the usual T-systems. Okay. Right. So, yeah, so looking back at our snake construction, we see that the loop parameters of successive lines in our snail are in minimal snake position with respect to each other. So, we come to the conclusion. Yeah, one can now prove the following assertions. First of all, in the tensor product of fundamental representations of the Youngian, so L plus 1 many, antifundamental and fundamental modules, there are Fibonacci of L plus 1 many composition factors, and one of which is the minimal snake module, which is just the product of the fundamental loop weights that we just saw. Yeah, so the fundamental loop weights of the successive lines in this snail operator. Okay, so yeah, so this is somehow what we would think of as a generalization of this Kirillov-Reshetikhin module WK, and yeah, so we had this kind of funny relation for the WKs that appear in successive lines in the snail operator. And there's a complete analog with this SN plus 1, this minimal snake in our snail. And I can prove the following relation, which looks like this. SP times S1, which is an additional line in the snail operator, either fundamental or anti-fundamental, depends on M. So M is just an additional index that I put in to make it either, yeah, so you see N of T plus M, and this big N is just 1 if T is even and N if T is odd. So I just put it in to have here like either fundamental or anti-fundamental line that I concatenate through my snake. To my snail. Okay, so the product, so we get this kind of other extended T-systems that I can prove from the extended T-system that I showed you, which look like this. SP times S1 equals SP plus 1 plus SP minus 1, completely analog to the story for SL2. And yeah, and these appear in this snail operator in the successively, yeah? So kind of fusion. And yeah, so the conjecture that I want to tell is that that only the minimal snake module SK remains. So the projector onto this cancels out. And this would be the completely analog to SL2. And that's it.
Immediate question: why conjecture 2.1 is conjecture if you can check it or just take n lines, like take n lines and check in Mathematica, for example, this?
Still be a conjecture. Check it in an example.
Okay, but in comparison that what was the previous in Snell construction, there was all possible zoo of this representation.
So let me
one term survive, so I don't understand.
Let me just draw the snake in the snail. Okay. So I take SF3 and k equals 4, and then it looks like this. Maybe this is a good end.
Is it one term in terms of projectors? Like, in terms of projectors, like in SL2 case, there was projector on the higher representation. Is it here, in terms of projector, is it only one term or many?
What do you mean? Which kind of projectors do you mean?
I mean, when you have Snell construction, you cut it, insert it unity. Yes, it's unity, it's sum over all possible projectors.
Yeah, but what I do is, so it's easier if you do it like this. So if you do it like this, so you take this T-system, which you can prove from the extended T-systems from the paper of Muken and Yang, and then you split unity like this, and then you try to see if it cancels or not.
Okay, but in terms of projector, it's more than one operator. It's not like NSA2 only higher representation. Yes.
It says that there is only one irreducible representation left.
I didn't say that. So this kind of snake module, this minimal snake module, it is irreducible as a representation of the Yangian, but it doesn't mean that it is irreducible as a representation of SLN. So this is the difference between SL2 and higher rank. So for SL2, any irreducible Yangian representation, or also the same for quantum affine representation, is like if it is irreducible as SL2, then it is also irreducible as affine or Yangian, and vice versa. So there's a one-to-one relation between irreducible modules. But for higher rank, it's not the case. So there are many more different irreducible modules of the Yangian, and these are these snake modules. And what you can prove is that any irreducible one can be kind of decomposed into a tensor product of snakes and maybe a direct sum. And that's what is explained in the paper of Mukin and Yang, actually. Okay, any more?
I think in addition to the snakes and snails, there should also be some snarks somewhere.
I was thinking about making a joke at the beginning of the talk that I'm going to be talking about biology more than about physics. There's one more question?
Yes, I just have a comment. I think as long as you are in SL2 at least, I think it would be interesting to consider the same properties of our matrix and to prove and to construct the Snell explicitly in some non-compact representation, for example, principal 3. Because in that case you could have a nice picture where all your operators are realized basically as integral differential operators on the complex plane. And since there is some literature, I mean, some things look familiar, and it would be nice.
Yeah, Hermann already explained that. I mean, it's a little bit different. Of course, it's a little bit more advanced, but yeah. So I would say that this probably has many applications in other directions.
So what would you have to do in order to prove the conjecture? I think all the representations.
Actually, I should just write down the projectors and put them in, and yeah, I should try to prove it generally, and yeah, so there's a good paper about how to construct these projectors, and I'm still on it, but yeah, for now it's just a conjecture. I'm sorry.
By the way, even if it's in status good checked conjecture, let's say it's even not rigorous, you can
put it in mathematics.
Beautiful. Then you can use it like ansatz to build this function omega. And if for example, start for three-side case, or even for two-side case or three sides. In three-side case, omega already known from the paper of Hermann, and you can just try and check whether it's correct or not.
Yeah.
The first question is how many functions are there?
Well, on three sides, I say.
Yeah, okay.
There are only two of them, yes.
There it's not, yes.
Yeah.
The answer was already known explicitly. So.
Yeah, right.
The answer is how many functions are there in the general case.
Yeah, okay.
That is the reason for all of this effort.
Yeah, okay, it's true. But answer is that actually conclusive or not? That's what is conclusion? As a finite number of omegas?
Conclusion is that only half of the RQK-Z relations really refers to this snail actually.
Well, taking
This is a problem. So I have like a last slide, very last. So this is actually, if anyone wants to know this Eng operators in more detail, it's here. So in general. But I think I didn't say what is R bar and R double bar, but it's just crossing transform of R and.
Actually, not the time to start this now.
Yeah, sorry. This is just how it looks.
Let's maybe go on with the next talk. Thank Henrik again.